Right, for the last part, we are going to talk about number bases. But we see that we can take a look at numbers in different ways. We can look at what happens when you divide something by something else. What happens with the remainder that we can use as modulo. This is we are talking about the numbers themselves. Maybe asking kind of a philosophical question of why do we use digits 0 up to 9? Why they add 10? Why are there 10 digits in our number system? That is because we have 10 fingers. But we count things, we usually group them into groups of hands. It's 1, 2, 3. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. When you have 10, then you will maybe put them into a box, and then you start a new set, and then you go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, another 10, you put that into another box, and then you repeat. So that's why there are only numbers up to 9, because once you reach 10, once you reach the next number, then you put everything into the box, you carry it to the next digit. And so that's more of a both philosophical question and historical question. Because there is a, I'm not sure if I have a meme there, or I don't have one. Yeah, if there happens to be an alien with only 2 fingers on each hand, then they would use the number base 4, because they can only count up to 4 with those 4 fingers. Kind of like a funny analogy or funny comparison. So yeah, we go back to what do you mean by number 99? What do you mean by those digits, those numbers? Why do we put one after another? And here, again, that's another clip that I suggest you watch during your free time. For the last digit, those things, there are 9 things there. There are 9 circles there. That's counting things. But the next digit, count how many sets of things, how many boxes of things are there. If you zoom it in, you can see that each one of it contains 10 things. Contains 10 balls. Let's zoom in here. There are 10 balls here. So this single dot, like the bigger dot, represents 10. It's a single dot, but it represents the number 10. And how many tens are there? We have 9 tens. That's the word 90s. 9 tens, 90s. If you see it out, ask how many things are there in total. We say, oh, there are 9 tens or 90 plus 9. So what we mean by 99? That means this digit by 9. If you split it out, then you will get 90 plus 9. And this 90 is simply 9 times 10. And again, if you ask why we use 10, again, that's the base. That's the number of sets. Each set contains 10 things. So that's how we integrate and analyze each digit. And that happens with 10. Like if you continue going, if you add another 9, I think this clip has fun. Like you get a dot like little big, and this each dot like would contain. If you zoom it in, you will get 10 purple dots, and again each purple dot contains 10 yellow dots. That's kind of a pretty big number actually when you think about it. Like, usually when you see number 999, you think, oh, that's 1,000. If you convert that to money, it doesn't seem like much. But if you think about, like, if I give you 999 bees in your house, how do you feel about that? Maybe dead. But yeah, that's a lot. But if you continue the trend, like this 9, as we all know from maybe elementary schools, there are hundreds. Third digit from the right, 1, 2, 3, the third one. Each digit represents 100. It's a big dot that contains lots of small dots, and each small dot contains even smaller dots. That's what it represents. And if you ask again, what is 100? It's this blue dot. And there are each of these blue dots. Each of these blue dots contain 10 purple dots. And you zoom it in. Or maybe we should we do it this way. You zoom in the blue dot, you get 10 purple dots. And each purple dot contains 10 yellow dots. So that's 100. That again, we already know. Right? This actually can be written as 10 times 10. So we get sets of sets. 10 sets. Each set has 10 balls, so 100. And if we keep going, and if you notice the pattern, you can see that whenever you write a number, let's say A, B, C, D, and let's start from 4. Then this is A times 1,000, plus B times 100, plus 3 times 10, and then plus D. We write it as, as powers, then 1,000 is 10 to the third. And then B times 10 square. That's 100. And then C times 10. And usually we just write 10, but here we just put a 1 there to make them the same pattern. And then just D times 1. Which is really 10 times 10 to the 0. But maybe that's confusing here, so just leave it as 1. But that's what is behind the base 10 numbers that we use every day. We know, you know 1,000, 110. But what they actually means is they are powers of 10. 10 to the power of 2, 10 to the power of 3, 10 to the power of 4, and so on and so forth. So that's the numbers behind the base 10. And once we understand that, the next question to ask is, can we replace that 10 by something else? 5? Maybe 3, maybe 2, maybe 16? Why do we go in base 10? Is there any places where we don't use base 10? Actually, in fact, if you trace back in history, usually people actually use base 12. As we know, we call it a dozen for some reason, right? Grouping is we putting in the group of 12 or as a dozen. And I'm not sure about English is whether there's a word for 12 square. But in Thai there is one. In Thai we call it lo. That's a dozen. And then a dozen of a dozen, there's a word called gurut. But that would be like 100 that we know here, that we know now. But back then, and they have a word for that. They use a different base, and then they have a word for that. It would be equivalent to. It's not the same, you know. This is equivalent to 10. This is equivalent to 10 square. And so on and so forth. And so yeah, the answer is yes. You can replace that by any base. It doesn't have to be 10. It's just 10 because we are used to doing that. But we gonna generalize that to here. The way we express base in, we express numbers in other bases is, and we have to put some extra symbols there, because whenever you say that 99, then everyone on earth is gonna assume it's 90 plus 9. It's base 10 number that we all use and love. But if you intend that to be a different base, then all you need to do is to put a parenthesis on the left and on the right and put the base. Just tell us what's the base. In this case, it's base M. And then we have all the number inside, all the digits inside. And those digits, there's one restriction though. Like for each base, for base 10, there are 10 different digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That means for base, let's say for base 5, and there should only be 5 digits. Maybe like 1, 2, 0, 1, 2, 3, 4. If you happen to use only one hand, if you count 1, 0, 1, 2, 3, 4, 5, get 5, you put it away and you start over. So that's those 5 fingers, those 5 digits are all you need. But the requirement is that each digit is between 0 and m-1. So in base m you have 0 to 4, in base 10 you have 0 to 9. In base 100 you would have 0 to 99. We will explain a bit why, but just for now, make sure that the numbers don't exceed m. Not even m, it has to be smaller than m. For this example, this is a valid base 4 number, like 1 and 1. It's not 11, it's 1 and 1 in base 4. That's a valid number base 5. And you can guess what year I made this lecture on. Just some note, like this one is not a valid number. Just like in base 10, you don't lead a number with 0. That's meaningless, that's weird. And again, sometimes you have to be careful of the digits. If in base 5, there should even be a number 5 there. 5 is too high. If there's a 5 and when they compute things, you see that 5 should be carried to the next digit. That's numbers. And then there are 2 things we can do for now. Like for the application part, that's gonna be later. But for now, if you just curious on, it's nice, we have different bases. Let's say we have different languages. Like I use base 10, you use base 12. How do we communicate back and forth? I don't have a picture, but let's say we human using base 10. We are trying to communicate with aliens with only 4 fingers, so they use base 4. How do we convert numbers back and forth? Well, the first answer is calculator, computer, whatever you have. But there's a way to convert numbers back and forth. Like the easy way is to convert number base 10, base m, any base to 10. Like as we saw above, like if you have base m, that means you have 1. Let's say it's base 5. If you are using base 5, you have 1, you have 2, you have 3, you have 4, and then for the 5 you have to carry that away. So that's you get one group of 5, 0, 0 left over. So that's 1 0 in base 5. Yeah, now we need the parentheses. This is number 5. And you can carry around, like to express 6, you have 1 big 5 and then 1 smaller one, so that's 1 and 1. So 6 in base 10 is 1 and 1 in base 5. So I don't call it 11 because it's not 11. It's just there are two ones next to each other. And you keep carrying this around. Right, so that's the concept of how you do that in base 5. And if you have numbers in base 5 already, let's say it's 1, 0, 5. Oh, I just made a mistake. 3 in base 5. Then yeah, that's just as in base 10. Like these numbers are the number themselves times the value of that digit. We start from 1, and the last one is also the last digit is always representing 1, representing a single object. Next digit represents that base itself. So in base 5, this one would represent a group of 5 objects. And then the next one represents a group of 5 objects. we have 5 of the smaller ones. So this one represents 5 times 5 is 25 objects. If you try to imagine that visually, you get 5 big groups. That's like 5 smaller objects. That one big group. That's what this number 1 represents. And then we have 0 times 5, which is nice, because that's just 0. And then we have 3, so it's 28. Let's use the formula to convert one way. Oh yeah, but just to make sure that you don't start with 1, right? The last digit is number 1. And the next digit is the base itself, the base square, and then so on and so forth. So lastly, we can convert. Before we go there, like if the base are smaller than 10, we can just use number from 0 to 9. We just don't use them all. Like in base 5, as you saw, we use 1. We use 0, 1, 2, 3, and 4. If you have base 2, you only use 0 and 2, 0 and 1. That's all we need. If you use base 8, use 0, 1, 2, 3, 4, 5, 7, or 6, 7, 8. Then what about base 12? Yeah, you can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you use 10, I mean that's 2 symbols, right? It's not 1. It's confusing. If you write that in base 12, then is it 1, 0? Are there 2 different digits, or they just a single digit? So that's confusing. And that means we don't use 10 in base higher than 10. And the convention is to replace it by capital English letter A. So this letter A is 10. You can think of them as 10 objects lying around. Then we need 11, of course, to use speed. So that's for base 12. And you can keep the same pattern here. Like for base 16, if you are using the base 16, like 0, 1, 2, 3, all the way up to 9. That's 9. And the A represents 10. B represents 11. C represents 12. D represents 13. E represents 14. And F represents 15. Yeah, there should be 16 symbols. 1 to 15 and then 0. So that's how you deal with when you have base higher than 10. Just add letters. So yeah, the ideas. And the popular one are 12 and 16, so it works fine most of the time. Unless you have like base 40, like 50. If you run out of English letters to use, letters in English alphabet to use, you could try. Oh, I don't know. So that's it. Like yeah, for instance, we have some examples. We can look at these slides then. And lastly, we can convert back from base 10 to any base. This is more difficult. It's not like that you can plug everything into a single formula. You have to consider them as just like division and multiplication. Like if you have 2 times 3, it's 6. If you have 2 divided by 3, that's going to take a while. You have to do the long division, or you have to do a long division. 3, 2, 0, 3, 6, 18, 6, and so on. That's a totally different process. That's tidy. That's not guaranteed to give you a nice result. Just keep this in mind. It's easy one way, but not the other. So yeah, just like this one. For any base to 10, you just plug in the formula. From 10 to any base, you need some kind of like algorithm to try that. But the next thing, there's still some fixed algorithm to attempt that. For instance, The question is short, right? Write 18 in base 2. But you have to check the slides to see that. Oh, okay. So you have to first kind of list what are the possible digits in base 2. You will have 1, 2 to the 1, 2 to the 2, which is 4, 2 to the 3, which is 8, 2 to the 4, which is 16, 2 to the 5th, which is 32. And then you get, oh, okay, that's the base we can divide. We're gonna need 2 to the 4. And then kind of like fill in the blank. Oh, we need one copy of 2 to the 4. Then let's see what else we need. We have 16. We need 2 more, so we need another copy of 2. So it's 2 to the 1. And then you have to convert that back. Like in base 2, this whatever is multiplied by 2, that represents the F digit in base 2. And so is that. So in the 5th digits from the right, we get the 1. And then there are some missing digits. You can see 2 to the 3rd is not there, 2 square is not there, 2 to the 1 is there, 1 is not there. And so that's how we convert 18 to base 2. And again, there's a fixed nice algorithm that you should follow. Yeah, but for now, just a quick recap of how you can accomplish that. So yeah, that's the end of the lecture.